We've seen some simple examples of recursion. Factorial, doing multiplication by doing recursive addition. These are nice places to start. But recursion is actually really a powerful tool, and I want to show you a very different way of thinking about recursion on a problem that's otherwise hard to solve if you don't think about it recursively. And this is to take a classic problem called the Towers of Hanoi. The story is that somewhere in a temple in Hanoi, there are 3 tall spikes on which there are initially 64 discs of different sizes all stacked together in decreasing order, with the largest at the bottom going all the way up to having the smallest at the top. And the goal of the priests in this temple is to move the entire stack from one spike to another one, moving one disc at a time, but with the property that they can never have a larger disc covering up a smaller disc. And there's a little animation you may be watching at the bottom here that's showing an example of that with a stack of size 3. We want to figure out, how would I write a program to tell the priests exactly how to move those discs so that they can move all 64 from one spike to the other. And I'm going to do a little demo to show that to you. So I want to demonstrate for you how to solve Towers of Hanoi, and especially how to use recursive thinking to do that. But to begin with, I'm simply going to show you solutions to Towers of Hanoi and see if you could figure out how to write code to describe the set of moves that would solve it. Let's start with the easiest case. I have a stack of size 1. Moving it is easy. I just move the disk. If I have a stack of size 2, I know I've got to move the smaller disk to the spare place while I move the bottom one, and then move it over. Pretty straightforward. If I want to move a stack of size 3, it takes a little more work because I got to move the top disk. I got to be careful not to cover up a smaller disk with a larger one. But once I've cleared the bottom disk, I can move it, and again move the top disk to the spare one so that I move the entire thing without covering up a smaller disk with a larger disk. Also pretty easy. But what about a stack of size 4? It takes a little more thinking because I have to really be careful here that I'm not accidentally covering things up. And it takes a lot more work to, in fact, expose that bottom disk, which I'm now ready to move. And now I got to get all of those back over again without covering a smaller disk with a larger one. And so that allows me basically to make that set of moves to get to that point. Great. Easy to write code to do this, right? Probably not. But if I think about it recursively, it's really easy. So what does that mean? I want to move a stack of n disks. And recursively, I would say, if I already knew how to move a smaller stack, what's my solution? Oh, that's easy. Move a slightly smaller stack to the spare disk. Now I can move the bottom disk and move that stack to the target. And what does it mean to move that stack to the target? Move a slightly smaller stack to the spare disk, move the bottom one, and move that stack. And I'll just keep unwinding that until I'm just moving single disks. Recursively, this is easy to see, and that leads to a very natural implementation. Okay, what you saw in that demo is that it's going to be hard, even if you watch things like moving a stack of 3 or a stack of 4, how would you write the code to do it? And then what you saw is, if I think about it recursively, it's actually really easy. Because recursively, what do? I solve a smaller problem. Move a stack of size n-1 onto the spare disk. Then I've got just one disk left on the bottom of it. I move that one, it's a simpler problem. And then I move that stack that I temporarily moved to the other side back onto the place I'm going to. Recursively, this is really easy to see. And so even though this looked like a very hard problem, it's very easy to write code to do it. And so there is, in fact, a little set of code that says, I got a function that simply says, print an individual move from the from stack to the to stack. And then here, notice what I've got. I've got a test for a base case. If I've got just a stack of size 1, I'm just going to print the move to take it from to 2. Otherwise, I actually now have to solve 2 recursive problems. So it's a little bit different. I'm going to move a smaller stack from the from to the spare spot. Having done that, I'm going to move the simple case to the place I'm trying to go to. And then I got to move that smaller size stack from the spare over to the to spot. But the code itself is really straightforward. And if in fact I go and run this on a stack of size 4, it gives me very nicely all of the moves I want to do to move that stack over. What I want you to see here are 2 things. One, I can have multiple recursive calls inside of a function body. It's perfectly fine. And two, this is a problem that I suggest is really hard to solve iteratively, but elegantly easy to solve recursively. And I want you to think about that notion of break it down into a smaller version of the same problem, assume that can be solved, build your solution with that and other simple operations, and let the recursion then unwind it to get to the solution that you want.